was very interesting because at the time, it looked like a really logical follow-on for some work I had done long before that it turned out he had never seen at the time. So we had a lot to talk about. I'm really very interested to see what he's done in the past couple of years. So thank you very much.
Thank you very much. It's a pleasure to be here. My name is George Wolberg. As Josh said, I'm a professor of computer science at the City College of New York. And this is joint work with Siavash Zokai at Brainstorm Technology, which is a software house here in New York City, not far from Google, New York. That is devoted to the development of 3D photography software. Okay, so I should say a little bit of history about this work. Almost 2 years ago to the day, I gave a Google Tech Talk at Mountain View about the subject of PhotoSketch, about Photo-Centric 3D modeling. And at the time it was early work in that area, and it was a standalone application. And last year at SIGGRAPH in August 2008, we presented some of those results to the Google folks, and they suggested, why not make a plugin for SketchUp? Okay, so since then we have, and I'm here to tell you about the developments in that area. And I'll show you exactly how SketchUp will help you make 3D models, lightweight 3D models that are phototextured in a very easy way. At the end of the talk, I'll also talk to you about some of the recent developments in terms of lightweight reconstruction of buildings from dense range data. So most of the talk will deal with the photo-centric work. The last segment will talk about recent work from range data. Okay, so let's begin. PhotoSketch is a photo-based 3D modeling plugin. And what that means is that we take several photographs of a scene, and these photographs are pretty closely spaced out, they're overlapping, and they will go into the PhotoSketch plugin to develop the results you see at the bottom, basically phototextured lightweight 3D models. Another example is shown here as well. And by lightweight, I'm talking about just a few hundred polygons, so this is very appropriate for web-based applications. In contrast to, say, the results you get from range data, which can have millions and millions of points. So there are many applications for this work. Of course, the phototextured models can be uploaded to Google Earth. It has applications for 3D car navigation systems, realistic sets for movies and video games, pre-visualization, architecture, of course, urban military planning, etc. So there are many applications. Now, PhotoSketch offers the following features. First of all, camera calibration, easy to use, automatic camera pose recovery from photos, which means that we can actually figure out where the photographer was standing, what's the position and orientation of the camera that took those photos with respect to the model that we will reconstruct. And of course, since it ties in with SketchUp, it has easy-to-use sketching interface and intuitive push-pull extrusion operations. And it allows for constrained drawing onto floating ground plane for convenient footprint and rooftop sketching. We also offer a rich set of tapering operations that exceed those that are available in SketchUp. In other words, we offer tapering to points, arbitrary lines, and curves. That's very helpful. And the main element here is that we're using photographs to help guide the sketching and help build the models. We also offer advanced texture mapping so that we can automatically detect occluded areas and paint them appropriately. So this is the workflow for PhotoSketch. There's basically two branches that you see here, the branch on the left and the branch in the middle of the slide. The left branch is just devoted to camera calibration. It's very important that we calibrate the camera before we perform this work. And the central branch basically shows that you have to collect overlapping scene photos and then recover the camera points for each and every photograph. And then those input photos, as well as the intrinsic camera parameters that we found through camera calibration, and the extrinsic camera parameters that we found through camera pose recovery, all get inputted into PhotoSketch plugin, which then helps create the lightweight photorealistic model. Okay, so let's begin by talking about camera calibration. In camera calibration, we recover the intrinsic camera parameters that include focal length, aspect ratio, principal point, which denotes the image center, and the radial lens distortion. Okay, so in order to introduce this, we basically start off with a very simplistic idealized camera model, which is the Pinhole camera model. And there you see a point, capital X, which is a 3D point that gets projected to the image plane as little x as the rays converge to the center of projection, which is point C. So the equation at the bottom basically says, we relate a 3D point in the world to a 2D point on the image plane through this matrix K, which is known as the intrinsic camera parameter matrix. Now, K, in the ideal simplified sense, only consists of information about the focal length F, but in practice it's a little bit more involved. And basically you see the matrix K here, which takes into account theta, which is the which is the skew angle between the axes, the x and y axis. It takes into account S, which is the pixel aspect ratio, and it takes into account C0, which is the components Cx and Cy, which are the coordinates of the principal point, which is the center. In the idealized world, of course, S is equal to 1, theta is equal to 90 degrees, and C0 is a 0. But in practice, that's not the case, and we have to solve for that. Another important element is radial lens distortion. So if I bounce back and forth between this slide and the next slide, you will see the difference between the distorted image and the undistorted image. Okay? The greater amount of the effect occurs at the periphery of the image. And basically to highlight this, you'll notice that there is a yellow line drawn on the right side. The two endpoints of the line are on the edge of the building. But if you look closely, on the left image, you see that the corner, the edge of the building, does not really sit underneath that line because of radial lens distortion. So our job here is to correct for that so that we can warp the image into an undistorted state, as shown on the right. So this is very important as well. And every camera, even if it's from the same model, will have different radial lens distortion. Okay? So we need to solve for that. So how do we do so? Okay, so that's the calibration procedure. We basically want to mount a checkerboard pattern, some test pattern, on a flat surface. And here you see 3 examples of different places you could mount the checkerboard, either on the wall, the floor, or a table. And then from that mounted checkerboard image, you would take about a dozen or so pictures from different angles and distances. And this figure here shows that, various different places you might want to consider taking pictures of that checkerboard pattern. You can see that they are scattered around different positions and distances. Okay, so there are some guidelines to follow in order to do a good job of this. Because if you don't do a good job of this, then the rest doesn't work as well. You want to make sure you don't have garbage in, garbage out, right? So it's important not to change the zoom settings or camera resolution once you do this camera calibration, or during the course of camera calibration. You have to stick with the same exact zoom settings and camera resolution. And these settings have to be the same that will be applied during scene capture. Okay, so in order to help with this process, it's useful to use the widest angle for a zoom setting so that you can guarantee consistency. Because when you turn off the camera and you turn it back on, how do you know how to get to the same zoom setting you had before? Well, you don't really unless you know that you're using the widest angle. That's one place where you can be sure that that's the same zoom setting. Of course, if you're doing this with these camera phones, of course they are all fixed focal lengths, so that's actually helpful for us. Okay, so there's no chance that you could change that. You want to also disable the camera flash to prevent glare and use a high shutter speed to avoid motion. So here are some examples of problematic images. You want to try to avoid this. You don't want flash reflection, or you don't want partial views of a checkerboard image. You don't want underexposed or overexposed images, or images that are out of focus. Because in all of these cases, it's going to have some effect on the accuracy of extracting features. We're going to have to extract features from these images. So assuming all goes well, then this is a window that you would typically find that pops up within the PhotoSketch plugin. It shows you the images that you've selected. Those are some basic examples of checkerboard patterns you'd be acquiring. And then it prints out some information about the camera and its focal length, principal point, and radial lens distortion that was solved for. Okay, so at that point, we've recovered the intrinsic camera parameters, we've done camera calibration, and we can proceed with the main branch. So the first thing we have to do here is to collect overlapping photos of the scene. The Again, there are some guidelines to follow there as well. So, as we said before, and this is critically important, you do not want to change the zoom settings or camera resolution. These are things you don't want to do. You do want to walk around with the camera in an arc around the subject while pointing the camera to the same part of the scene. So that's an example of something you do want to do. You also want to have the distance and angle between consecutive images be small, so that we can have a lot of overlap between consecutive images. Because ultimately, under the hood, what we're going to do is extract features from these images and track them from frame to frame. You want to avoid standing in one location and panning the camera, because that limits parallax and offers little 3D information. So by panning the camera, I mean, imagine that the camera was sitting on a tripod and all you did was you rotated the camera and pivoted around the vertical axis. You want to avoid that. And we mentioned parallax, so what is parallax? We refer to parallax, or at least it manifests itself, as the apparent displacement of objects when viewed along different lines of sight. So here you have an example of input image 1 and input image 2, which are two images that were taken by taking a snapshot, walking with it to another snapshot. If you simply overlay them, you will notice that the objects in the distance pretty much are in one place, but the objects nearby have been displaced a great deal. So you'll notice that nearby objects have larger parallax than more distant objects. And through this, we can infer depth by measuring image displacements between corresponding points in the images. In general, the greater the displacement, the closer the object. However, this effect does not apply when the images are taken from a single center of projection. So that's why we want to avoid this case, which is shown here again. You don't want to stand in one place from single center of projection and just swivel the camera around. Okay, that violates the ability to get parallax, which we need. Parallax is our friend. Okay, we also do not want to walk in a straight line towards the sea because that creates ambiguity between zoom and translation. So, the more chaotic you are in terms of taking these pictures, the better. You just want to make sure that you don't take them too far apart so that you can match features in one and features of the other. And if you have 50% overlap in these photos, that's great. Here's another example of guidelines to follow. And the reason I'm spending so much time on this section of guidelines is because it's critically important. If you don't do this right, you will have problems later. You do not acquire images over concave paths because they may share a single center of projection and produce only marginal parallax. So the example on the left is an example of something bad. It basically mimics, standing in one place and just, swiveling the camera around. That will have minimal parallax. What's better is what's shown on the right. Move around the room and collect the photos. Okay. And finally, you want to avoid motion blur to improve feature matching accuracy. And you want to avoid glass buildings if possible to eliminate independent texture. Now, I should say, okay, that sounds harsh, but if you look at the image on the right, you will see that there's a reflection of the building on the lower right side. And the problem is that as you walk around, that building tends to move greatly. It's a reflection. So you might be extracting features of something that's not truly part of the building. But it's not as bad as it sounds because as long as there are enough other features on the building that stay rigid to that building, then you're okay. So, I'm just pointing out some of the things that can go wrong with caveat.
I once went to a presentation on a scanning device where they described going to an Air Force base to scan a helicopter. And when they got back and looked at their data, they realized they couldn't see the airplane behind it because it was stealthed. They got a call from the Air Force the next day asking them to destroy the data.
So stealthy materials don't work well. Okay, so once we acquire the overlapping photos, we have to go ahead and perform camera pose recovery. So in this case, that means that we're recovering the extrinsic camera parameters, which include the camera position and the orientation that's associated with each image. Simultaneously, like the flip side of the same coin, we also recover a sparse point cloud. In other words, we said before that we extract features from the images. Now these features can be triangulated into 3D points. So every feature that we find in an image has a correspondence to a 3D point out there in space. And so we are finding both things together. Okay? It's meaningless to talk about recovering a camera pose unless it's relative to what? Relative to the model or the object you're recovering as well. So we're doing both things. We're getting the camera position and orientation for each image, and we're getting the 3D positions of extracted image features. And the purpose of this step is to bring all the photos into a single reference frame. There is a feature in SketchUp called Match Photo, Photo Match. The current one is Match Photo. And there you have to basically do this by hand. Every image that you bring in, you have to manually specify vanishing lines and specify how one coordinate system relates to the other, which doesn't really scale well when you have a lot of images. This does it all automatically. So it's an important virtue of PhotoSketch. Here's an example where we have 5 input images. And what you see at the bottom are 5 recovered camera poses. Those are denoted by the frustums at the bottom left. And simultaneously, you see the sparse point cloud on the bottom right. So you get those two things. I consider them the flip side of the same coin. You have to get them as together. And that's basically what we get from these 5 input photos. Now, as I said, the purpose of this is so that you can draw on one image and then properly see that drawing in the other images, in different viewpoints. That's only possible once you do camera pose recovery. So as you see on the upper left, let's say we are sketching out a rectangle which denotes the rooftop of one building, and then we jump to a different frustum, one that corresponds to the camera that took another photo or another photo. And you'll see that that same rectangle that you drew on top of one photo is properly displayed on the other photos as well. So we need multiple images to facilitate total coverage of the scene in the presence of occlusions. In general, you cannot see the whole building in one view. You want to walk around it. And furthermore, not only do you get more coverage, but you basically deal with occluders. So things that are occluded in one image are generally visible in another image. And we can use that, and we refer to that as diminished reality, and I'll talk more about that later. So we use multiview geometry to help compute this camera pose recovery. As you can see here, there are different elements to the work that I'll talk about. Multiview geometry is the first element. You also have floor alignment, which we need to do. Then goes the sketching of the footprint, push-pull interface, and advanced texture mapping. So we'll begin now with multiview geometry. So in this case, in multiview geometry, what we do is we automatically extract salient features from the image. And then we perform feature correspondence among image pairs. And we will then initialize a camera poses structure from the first 2 image frames. And we will recover the camera poses of all successive frames. So the first 2 help us bootstrap the process, and then we move on from there. And we perform bundle adjustment to distribute the global error. So if we talk about extrinsic parameters, we have to look at this slide and better understand that. On the right side, you see a 3D point capital M, and it's represented in the world coordinate system. But it has another representation, M sub cam, in the camera's coordinate system. So the second equation we see there, M sub cam equals, okay, that basically reflects how we get from 3D point M in the world coordinate representation to the camera coordinate system. Now, the next line, little m, which is a 2D point, the 2D position of that 3D point, can be represented as k times m sub cam. Remember k, we saw that before from the intrinsic camera parameter matrix. So k gives us the intrinsic parameters, but how do we get m sub cam? Well, we see from above that there is a relationship between m sub cam and n, and that's given in terms of this matrix we see here. Pointing to it with the laser pointer. So we end up with this equation. You see here k times this matrix, which is in terms of rotation and translation, times n, which is a 3D point. So you can see how we really need all this information. We need the 3D point, we need the extrinsic information, we need the intrinsic information, so that we can specify how does that 3D point become that 2D point on the image plane. We solve for the intrinsic camera parameters through the camera calibration model. That part is known. What is unknown is the R and the T, the rotation and the translation. So that's what we have to solve for. So we have to solve for that unknown R and T, and to do so we compute the motion of pixels across all of the 2D input images. And pixel motion is computed only on the salient points. So a feature transform is used to compute the feature descriptors for those salient points. A popular feature transform is SIFT, scale invariant feature transform, and there are many variants on that, and other scale space variations as well. So these descriptors will be used to match points from one image to another. So you see how there's computer vision work involved here to basically infer the camera positions by extracting features. Here's an example on the left of some features that we extract on one of those images. It's a little bit hard to see, but there are a bunch of dots sprinkled on that photograph. Those dots are the extracted features. Then in the next image, we track those feature positions, and they are connected by those yellow lines. So we see how we are able to track features from one image to the next. Now, what you see here is basically the kind of bird's eye view of this whole process. In frame 0 and frame 1, we've done the tracking of those features. You can see the 3 points shown in frame 0. Let's see if I can point it here. Okay, so there are 3 points shown in frame 0, and they are matched into frame 1. That's what those arcs represent, that we've actually matched them. And we initialize the extrinsic information for frame 0 with an identity matrix for the rotation and a 0 vector for the translation. Okay, so that much we have to assume. That's kind of like a bootstrapping process. We'll assume that. And we will then solve for R1 and T1. Okay. Now we can do so by applying a QR decomposition of an essential matrix to recover that R and T for the first pair. Okay. So what that does in the end is it basically allows us to have these two camera poses known, and we can take those 2D positions and their camera poses that are known for those two frames, and then triangulate them back to 3D points. Okay, so if we know the camera poses for the first two images, and we know these 2D positions, we can triangulate to get the resulting 3D version of those 2D points. So that forms these points in the point cloud. Then we go further and we say, okay, for those features that we have already found, can we track them again in the next frame? Okay, so we track them again in the next frame. And we use a 6-point ransack algorithm to build up these unknown rotation and translations for all of the successive cameras. So ransack algorithm is fairly well understood. And so that helps us get the rotation and translation for all those successive camera poses. Furthermore, of course, there will be some features that fall away, that can't be tracked anymore. So there will always be new features that come in that then get tracked from that point on. So that's what we call sequential updating. We build up a denser and denser point cloud as we consider more and more of these images. Okay. So bundle adjustment is used to help distribute the error of the camera pose and structure. And in general, what we're doing here is we're minimizing the reprojection error. So in this equation, you see that we have capital M, which is a 3D point, and capital P, which is the projection matrix, which is built up of that K matrix, and the unknown R and T. And we have to find out the unknown R and T to best minimize this expression. Now understand that this 3D point and this projection matrix should fall on the 2D image feature, which we have found, using SIF, let's say, or some variation of it. So we want to pick the P and M to minimize that. Okay? And that's ultimately what we find. And here are some examples of that. Imagine we took about 24 images around the building on the campus of City College of New York. So it's a large Gothic structure. And we walk around it taking multiple pictures. And here are some of the pictures we've taken. And you can see that those pictures that we've taken, we have found for those 24 or so images, those white dots. And those white dots represent the position of the camera. Now, associated with each white dot, you see red, green, and blue axes. That represents the orientation of the camera. So without GPS or any other assistance like that, we are automatically able to figure out the position and orientation of the camera that was held by the photographer as he took all those pictures. Now, what you also see is this sparse 3D point cloud as well. So, they're the flip side of the same coin. You use one to help find the other. And that's basically what camera pose recovery is about. Now, the next step is floor alignment, where we have to recover the ground plane necessary for sketching the footprint. It's important to point out that because when we started this process of camera pose recovery, we assumed one thing. We assumed that we had to use the identity matrix for the rotation and the 0 vector for translation. That essentially means that we have a camera that's coincident with the origin of the world coordinate system, and it's looking straight out at the horizon. But we know that's not necessarily the case. But for the purpose of getting this process started, we assume that. As a result, we have what's shown on the left. The initial camera is looking straight out the horizon, and everything we reconstructed, might be rotated. It might look off. What we know, in fact, is that the building is generally not sitting like this. It generally is sitting so that the plane is, the floor of the building is on the ground plane. And it's the cameras that could be swiveling. So we need to be able to align this, and that's called floor alignment. Okay, so we do so by selecting at least 3 corresponding points manually in 2 views that lie on a plane. And since pose is known for each of the cameras, we can triangulate these 2D points to get 3D positions. A plane is then fitted to these 3D points. And the normal of that plane can be rotated to align itself with the normal of the floor. That means that the normal of that plane can be made to point straight up. Okay? And the user can select points that lie on any plane that is parallel to the floor. Even though we call this often a footprint and we think that this has to be on the floor, realize that oftentimes we don't actually see the floor because it might be occluded by cars or people or whatever. So we can use any other plane on that reconstructed photograph, basically. That happens to be parallel to the floor. Okay, so we have a little video segment with audio.
You must establish 3 correspondence points among the 2 displayed images. These points must lie in a plane that is parallel to the ground. A magnified view of the pixel neighborhood is shown about the selected point to help you accurately pinpoint the corners. The established correspondence among a pair of points is depicted by a yellow line. This process is repeated 2 more times. When you are finished, click the right mouse button and select Done. This places you in the position of the photographer that took the first picture. Notice that the aligned floor plane is now visible. By zooming out using the standard SketchUp navigation tools, we can examine the results of camera pose recovery. Notice the positions and orientations of the set of cameras that were used to acquire the input photos. Each camera is depicted using a frustum. Camera pose recovery occurs simultaneously with the recovery of a sparse 3D point cloud as shown here. Each 3D point in the cloud corresponds to an extracted image feature that was matched among multiple views.
Okay, so once the floor is aligned, then we can proceed with sketching the footprints. And the photographs will serve here as drawing stencils. And the sparse point cloud that we found earlier in camera pose recovery will help validate the footprint placement. We will be able to snap to those 3D points.
Click on the Snap to 3D Point icon and select the 3D point to snap the floor plane to that position. Then, select the 2D rectangle icon to begin sketching a rectangular footprint by clicking 3 points on the corners of the building facade. Notice that this drawing mode is constrained to the snapped floor plane. A magnified view of the pixel neighborhood is shown about the selected point to help you accurately pinpoint the corners. Rectangular footprints are common for many buildings, which is why we use them here. This process of snapping the floor plane and drawing the rectangles is repeated for all of the footprints that are visible in this photo.
There you see that we always snap to the relevant 3D point that's associated with the rooftop.
When you draw the first edge of the rectangle, try to draw the edge along the vanishing lines. In this example, they tend to lie along the edges of the windows. Our system allows you to switch from one viewpoint to another. Due to camera pose recovery, a footprint drawn in one viewpoint will appear registered in the other viewpoints and will be aligned with the sparse 3D point cloud. Notice that the footprints were each snapped to the heights of the selected 3D points.
So there you get a feeling for how sparse that point cloud is, but nevertheless it is helpful for snapping the points there that allow us to constrain the drawing to a plane on the rooftops. So the next step is push-pull interface. This is familiar with all SketchUp users. So we have extrusion operations that we'll talk about first.
Click the floor layer icon to hide the floor. Click the point cloud layer icon to hide the 3D point cloud. Now, click the push-pull icon and select the face to extrude. This extrusion operation needs to be repeated to all footprints to create 3D volumes that are embedded in the scene. You may quickly switch from one viewpoint to another by clicking on the next camera and previous camera icons. It's important to note that if you dive into the scene beyond the textured frustum, you can see the untextured 3D models. In this example,
So now what we'll do is we'll talk about the paper operation.
we see the model from the same vantage point as the photograph. Notice that the alignment is perfect. Now, we jump to a new vantage point to see the roof. We use the Taper to Line tool to insert a line so that we can lift it to taper the roof as shown here. We now repeat the process from a different vantage point to taper the tower to a point. To verify that the geometric refinement correctly matches with the photos, we view the refined models from the different frustums.
So one thing I wanted to point out there is that we introduced the Taper to Line tool and the Taper to Point tool. And in the Taper to Line tool, you'll notice that you can orbit anywhere you want to see the proper view, the most convenient view of the top. You draw the line, and as soon as you start pulling it up, so that you can taper to that line, you get pulled back to one of these views from the frustum, so that you can use the photograph to help guide you as to how far you should pull that line up. And the same thing applies to the Taper to Point tool. You put a point down. As soon as you start pulling up on that point, you hop right back to this view automatically, so that you know, let's say in this example, how far you should pull that apex up. And then we have advanced texture mapping, which allows us to project photographs onto the facade to assist the editing process. And we exploit GPU processing for occlusion detection and image fusion. So on the left, what you see here is something that you would typically get in SketchUp, whereby you project an image onto the building. The problem is that the image was taken from the camera at the ground level, looking up. So the image not only paints the front facade of the building, but it actually extends beyond that and intersects with the side wall of the next building. Okay, and there's no way of avoiding that unless, of course, you detect this occlusion. And we use GPU processing to do that in real time. And that's shown on the right. So those areas that were detected to have been occluded can be painted with a neutral gray color instead of having to deal with this undesirable texture on the left. So now that we have that, we can upload the models onto Google Earth.
One main application of our plugin is for users who want to add their content to online mapping systems. The user can georeference their model by aligning the model footprint with georeferenced satellite imagery and then uploading it onto Google Earth. Notice that translation, rotation, and scaling is necessary for proper alignment. Use the native SketchUp tools to perform this alignment.
We want to make sure that the building is not underground, so we will have to lift it up a little bit. There we go.
Can you use GPS information stored in the
Here we see the result of an uploaded model on Google Earth.
Model?
This model was completed in approximately 24 minutes. 3 minutes for automatic camera calibration, 1 minute for floor alignment, and 20 minutes for modeling. On average, our models typically have between 50 to 100 polygons. Such lightweight 3D models are highly suitable for transmission and rendering on web-based applications such as the Google Earth application shown here.
Here are some more examples. These models typically have no more than 100 polygons. They're very lightweight. Of course, you could put as much detail into it as you want. You don't have to get by with Yes, you had a question in the back?
Yeah, I was wondering if you could position the models at least roughly on the map using GPS data from the exit headers of the original photos.
Well, yes, the question is, can you position these models automatically using the GPS information that's tagged with the photo? Yes, there's no reason why you can't. Do we do that right now in this PhotoSketch plugin? No. but there's nothing to stop us from that.
Most of the consumer cameras, they don't have right now at least the GPS tag information. So.
Right. Yes, because that's correct. Most of the cameras don't have that information on a consumer grade level. And we really are targeting that market right now because we started out this whole work focusing on laser scanners. But unfortunately, most people don't have access to $100,000 pieces of equipment like that. So we said, what does everyone have? Well, they have these consumer grade cameras, and we're trying to work with that. But yeah, nothing stops us from using GPS information
Because actually, cell phone cameras more and more do.
Right. So that's something that we would add on. It's a good suggestion. Here are some examples that show the lightweight feature that we have from these models. And with 108 polygons, we have these renderings. These models are created. 82 polygons for that building. This other building had over 500 polygons, only because we wanted to have some more details there. One thing you'll notice on this example is that you do see the frustrums, which denote the camera positions and orientations. So that's something else we could lay down on Google Earth. Not only the models that we're building, but also the positions of the cameras that we use to take the photos of the models. That's something we don't see, used at all now, but it's something that can be made available. It's in a sense a form of geotagging. Not only do you say where you are, but like here you can see what angle were you even holding the camera when you took those pictures. Now, for those of you who use SketchUp a lot, of course, you know about match photo. And in that case, the user must align guidelines to vanishing lines of the scene. And so this is a useful tool, of course. On the left, you see the initial configuration of match photo. By the way, this was called Photo Match in SketchUp 6, and it's Match Photo in SketchUp 7. Okay, so we have the initial configuration shown on the left. You see this somewhat confusing array of grid lines there. But the user is expected to move, the grid lines to coincide with vanishing lines. So let's say the red ones there, are moved to coincide with one vanishing line. The other pair is moved to coincide with another vanishing line. So it takes a bit of work, of manual effort, to set this up on the part of the user. Now the disadvantages are, well, we just said, it's manual specification of vanishing lines. It has to be repeated for every photo. Whereas in PhotoSketch, we don't ask the user to set any of that up, it's done automatically. Because we have to extract the features from the image and do some math and figure out the camera pose ourselves. So we don't ask the user to intervene there. This also requires at least 2 vanishing points to be visible in the scene. And that limits the set of photos that can be used. I'll show an example in a moment where that would not apply and you couldn't use match photo for that. Also, it requires the coordinate axis of each new photo to be manually aligned with the existing axis. So that means every time you want to consider another image, you have to go ahead and align the coordinate axis of that new photo to the old one. And so this doesn't scale efficiently when you have a large number of photos. Here's an example where match photo, let's say, would not work. There are some scenes like this, which is an image of the Guggenheim Museum on 88th and 5th here in New York City. And there are no lack vanishing points and not even planar surfaces here. So there's 3 images that we took here. 1, 2, 3. So we were standing across the street from the Guggenheim on the edge of Central Park and we took these photos. Notice also that the color on the building, the texture itself, is very dull. I mean, very few features you can track on that. Yet we get this. It's funny because when I first saw the output of this, I thought, oh, this is a SketchUp rendering of the building. Then I realized, the colors are exactly the same from this. You give phototexture with the color, it just happens to look like it's one of those sterile renderings. Anyway, so you see there, you can recover the model. On the bottom, you also see the frustrums for the 3 images that we took. So what stands between that model and those frustrums is Fifth Avenue. Now, when we put that back on Google Earth, unfortunately, there's so many trees from Central Park that block you won't see clearly those frustrums as they're overlaid on the dark areas on Google Earth. So I didn't bother showing you that. But you could, in general, take any of these models and frustrums and put them back on Google Earth and see not only the building there, but also where these pictures were taken and the orientation of the camera. So these are additional PhotoSketch features that we have. You mentioned dynamic texture mapping with occlusion detection. I showed you an example of that earlier. We also have diminished reality, inpainting, and clone brushing. I'll say a few words about that now. First, we'll start out with dynamic texture mapping. I want you to concentrate on the top half of the screen. The idea here is that from any arbitrary view, so you could orbit to any convenient position, and you start pulling down on these footprints that you made, and immediately you get the images properly texture mapped onto that building. So that's what we call dynamic texture mapping. From an arbitrary view to immediately texture map that. As opposed to what you see on the bottom, which says that you're limited to only the frustum views in order to see the photograph alongside the model you're extruding. And in that case, it's not really even texture mapping, it's just overlay. You're just overlaying the image with the model that you're building on the bottom. But because of dynamic texture mapping, you can orbit to any arbitrary view and do this operation. So that's very convenient. And at the same time, we have automatic occlusion detection. So as you see, there are clearly marked gray areas, which denote that you would not have proper texture mapped there. Now you do see some bad texture on the roof of the building on the top. But that's only because we didn't finish the model, and we're just mapping the image onto a sloped roof. When in fact there are other elements on that roof that we have to begin modeling. Another important element of the work is diminished reality. You might have heard the term augmented reality, where you actually add things on top of the photos. Here we're trying to take away, so we call it diminished reality. And the idea here is that you have 3D objects standing in the scene that are occluding your buildings, okay? And we want to get rid of those objects, so we want to diminish those elements. And how do we then deal with that problem? Well, those pixels that lie on that 3D occluder can be thrown away and replaced with pixels that seen from a different angle. So here's a good example of that. Here you have 2 images, slightly different images. And on the left you see, on the right you see the street lights, right? Pretty close to the center of that image. So we don't want to use those pixels on that street light to be used to paint the building. But of course, from a different view, we don't have that problem. So, we can always throw out the pixels we don't want and put in the pixels we do want. And we can do so, as shown in this case, by, let's say, taking out that person in the lower left corner of the image by kind of, selecting a boundary around that person, and then replacing the texture from another view. So right now, it's kind of manual to select what part you don't want and replace it with another view. Of course, if we're a little smarter about it, perhaps what we would do is, like some sort of median filter, since you have occluders that might be present in one image but not present in several others, and those other several images would inform us that we should be using those pixels for the occluding on. Right now, it's a manual exercise. Here's another example with street lights. You could outline it and replace it with pixels taken from another view. Now, inpainting is kind of related to diminished reality in the sense that, yes, we are taking out elements that we don't want, but there are no other views that would tell us what values they should be, because these elements are so close to that building. You might have a gutter right on that building that there are no other possible views that could have told us what's behind that if we wanted to take it out. So, so this is kind of related to some SIGGRAPH work that was published in recent years, where you can suggest, to borrow the pixels from neighboring areas around that outlined region. So that would be called inpainting. Now, I say all this because these features, these 4 features that are listed here, can only be implemented suboptimally using heavy file I/O to to move textures or materials back and forth between SketchUp and the GPU. And it would be nice if we had access or modifications made to the SketchUp API that would allow us to do things more efficiently. So this next slide is kind of an appeal to the SketchUp development team, the wish list we have, for modifications to the SketchUp API. And these are some of the suggestions. Give us a way to have a get or set method to read write RGBA material values. We want to be able to write those pixel values directly without having to, take that, save it away as a file, do processing outside and then bring it back in. That's really inefficient. So we want to avoid that I/O-intensive manipulation of pixels by external programming. We also want the ability to map the texture materials to the GPU memory to support dynamic texture mapping while modifying the geometry. And we want to have a method to set the SketchUp axis in Ruby, because Ruby is a programming language we use for all this. And we want to be able to do this so that we can improve our interface to directly set the axes once we have enough information from the floor line. So if these methods were available within the SketchUp API, that would make our job a lot easier. And it would allow us to take what is currently real-time operations in our standalone program and make them real-time operations in our plugin for SketchUp. Right now, they're not real-time in the plugin because of these drawbacks. So something that would take 1/30th of a second to implement, to render, now might take close to a minute, because of all these heavy big files that have to be pushed back and forth, and it's just a little bit inefficient. Here's another very interesting application for dynamic text mapping, which we call it depth through focus. At the bottom of the screen, you see that we are pushing the wall of the building back and forth. And on the top part of the screen here, we see what happens when we project all the images onto that wall. Notice that you go out of and into focus. The focus is only good and sharp once the wall is at the proper depth. When you start moving the wall back and forth and you're not quite sure where to put it, then all those images kind of inform us that you're at the wrong depth because they're all blurred. So, this is like standard, computer vision work with, depth and focus. Well, we can use that to help inform us what is the right place to put that wall. So, there you see it again. So, right now, that's something that can be done with dynamic texture mapping. Although it's done manually, the user has to kind of play with that. You can imagine a case where this could be done automatically. You let the program walk through this, and it's kind of like autofocus on a camera. Just pick the right depth so that you have the sharpest focus. So again, those things would be possible for the dynamic texture. So here we have it. So the disadvantages of existing photogrammetry solutions is often manual camera calibration, where the user has to match points and lines among all photos or find vanishing points. That's typically the setup you have in Match Photo, right? It's somewhat difficult to scale up for a large number of input photos, and modeling is done by inserting 3D primitive objects into 3D space, which sometimes is a little bit awkward and clumsy. And in PhotoSketch, we have fully automatic camera calibration, we have fully automatic camera pose recovery, and we have automatic texture occlusion detection, and it's a great tool. So we encourage you to try it. I'll give you more information at the end of the talk to how you can get a copy of this. If I have a few minutes, right?
Yeah.
Okay.
Do you want to take questions, or?
Yeah, I guess what we could do is we could take some questions now, and I guess this would be a good point.
Okay. Well, thank you very much. That was. If we have questions, either locally or remotely. One locally.
You mentioned the radial distortion is different for every camera, even of the same model. Is there any chance that for a whole class of models, your iPhone camera, that they're close enough so people wouldn't have to do the manual calibration?
It's possible. We have to look more close. We have to look more carefully into that. The question was, can we say for a class of cameras like the iPhone cameras, can we approximate that with one set of parameters for radial lens distortion? It's something we have to look more closely at. And we found that we just go ahead and play it safe. We want to do a good job, and we take our time to do camera calibration on each and every camera, even when it's the same model.
And on the occlusion occluding object removal. I mean, maybe I'm missing something, but it seems like you could say, well, here's the bounding box of the object I'm sketching. Throw out everything outside that bounding box. And then the street light would vanish.
Okay. So let me repeat the question.
Okay, so when you're doing the diminished reality, you're getting rid of the objects that are occluding your scene.
Right.
So you had that street, that lamppost standing there, which you actually had to outline and remove. It seems like if you were to say, well, here's the bounding box of the building I'm sketching. Throw out all the points outside of that. Take them out of the scene.
Okay, so the question is,
easier user interface.
So the question is, can we simplify the user interface for diminished reality by specifying the bounding box of the object that we are
You care about.
that we care about? That would seem to be a reasonable thing to do. Yes.
Yeah, but the thing is that if you're more accurate about the boundary, you use more pixels from the good view instead of using from the oblique view. So if you draw a bounding box, then you use pixels from the very oblique angles, and then the pixels are going to be more distorted. So as much as possible, use it from the right view.
Right. So so the comment was made that we basically want to avoid using the pixels from the oblique views as much as possible because they have more tend to produce more blurring, and so we want to use them from the view that's more head-on.
But you could still determine that, right? And you can still find the the camera vector that's most 90 degrees to the texture that you're trying to restore detail on. You could choose the best texture to fill in.
Right, we could choose the best texture based on the angle. Yes, because we have the information from the model, we know the camera port recovery, so we know which direction we're looking at. We generally use that. In practice, we do something like feathering where it's a blended average.
Yeah.
So that's what we do. So I put up some information on this slide. PhotoSketch is been developed at Brainstorm Technology. Here's the URL. The plugin will be launched by the end of June 2009, right, so at the end of this month. You can email support@brainstormlc.com for questions, and we're encouraged to try it out. And ignore the information at the bottom. If you have additional questions you want to ask me, you can send me an email directly at wolberg@cs.ccny.edu. So I'd be happy to answer more questions about that. That's the best way to get in touch with me.
Okay. Are there any other questions? Maybe Boulder? Oh,
Have you looked at all at, actually I really like the idea that this is lightweight, that you have very few polygons, but have you looked at if someone wanted to make a very high-end rendering, like at recovering like depth maps, some relief off building facades, for example?
Using photographs?
Yeah.
You know what, because I had another segment of the talk, I'm committed, but time is not committed, where we used laser range data, and we were able to get some lightweight results, and these are some examples of them. We had dense inputs, and we created these lightweight models on the left. You see here, or here, this is the inside of some theater. We had millions of points from laser scanning on the left, and we reduced them to virtually nothing on the right. That's subject to some ongoing work. It's still very preliminary. And it doesn't deal with PhotoSketch because PhotoSketch is exclusively photocentric. It's only based on photographs, not laser scanning. But we can talk more about that offline.
Someone asked about mobile phones and pictures from mobile phones earlier, I think. Are you looking at that using GPS-enabled phones and stuff? It would seem you could get a pretty good guess of your orientation just from the accelerometers in there and all that. So.
It's true, yes. That's a good point. Should we be looking at the accelerometers to get some estimate for orientation? We haven't done that yet. We focused on these good cameras that don't have any GPS information on them or accelerometer, just conventional cameras. That's what we focused on now. But you're right that we should be moving towards looking at photographs taken from cell phones and using accelerometer information. That's the next stage.
Yeah, I think one can imagine, having a crowd simultaneously take pictures of something with all of their cell phones, upload all their data, and give them, create a model of what's happening right there.
Right. So it's that's another good point.
It'd be a lot of fun.
Yeah, a crowd of people taking
As long as
photographs.
nobody moves.
In full motion video.
Well,
Perhaps in real time.
one other thing that's of interest is also, there's a lot of street view data out there, right? So imagine that you take a picture, of some area, let's say you're in Times Square and you take some picture. Can't you, use the GPS information to know roughly where you are, and then find from the street view data that's available on Google servers, what's the best match? I just took a photograph. We've got all this data because you've already gone down the streets taking photographs of all the scene. Can't we match that up? And can't that inform me about my position and even, some other information that we want? So we would tie in, the photographs that you take with your camera with the street view information, doing matching, and
The
it
GPS
helps
from-
place you more accurately.
Yeah, the GPS from the cell phone is not very
Right,
accurate.
because
So
that's right. The GPS from the cell phone is not accurate, but here you'll be able to more, carefully pinpoint exactly where you are by matching your photograph versus the street view data that you already Google will enhance. So that would be another problem.
Is there anything else? Okay, well, thank you very much.
Thank you.
George, that was great.
Thank you very much.